All right, good morning, everyone. We're going over Lab 9, Earth's greenhouse effect. So last week we went over the different things in air besides oxygen and nitrogen, where 99% of it is nitrogen and oxygen. There's that 1% that still takes up the air that within our atmosphere that has an effect on the amount of heat that's trapped in. And some of it is CO2, methane, water vapor, things like that. And those are greenhouse gases and that makes an effect and traps in heat really well. But first, if we're thinking about weather versus climate, and what does that mean in terms of how does it react within our atmosphere? So what's the difference between both of those? If you don't like the weather, you can just wait 5 minutes. It's very temporary, it moves very fast, and it changes from day to day. If you don't like the climate, you should just move, because climate is very location based, and for an area it's very predictable and it doesn't change all that much. So the climate, it changes very, very slowly. So if you don't like it, you should move. So again, climate, location based, very location based. It depends on the latitude, how far away from the poles you are, their altitude. Are you up in the mountains or down by the valley? What's upwind? Are you near oceans? Is there a warm ocean wind, or are you in the middle of a wide expanse of land? We know that climate, it changes very slowly, so it's very predictable, and that's the same reason why if we can predict that Phoenix is going to be warmer than Fargo, is the same reason that we can predict that we're going to have a warmer future, just based on the data that we've been seeing, the CO2 concentrations and the temperatures that we've been recording over time. So have we ever wondered why summer is warmer than winter, day is warmer than night, Phoenix is warmer than Fargo? We can all attribute this to heat budgets. The amount of heat going into a system minus the heat going out is our change in heat. So if we're thinking about summer, summer days are longer, so there's more heat going in and there's less heat leaving. So our change in heat is going to be higher than winter days, where the amount of hours in the day is going to be lower, and so the amount of heat going in is lower, and the amount of heat going out is lower, so the change in heat is lower than that of summer. So thinking about this heat in terms of the electromagnetic spectrum, as we increase in wavelengths, as we go across, if we're thinking about the visible spectrum, as we get closer to infrared energy or heat, it gets the types of different energy. It gets warmer as we get closer to infrared energy, but the increasing energy also decreases, but our wavelength increases. And this, if we're thinking about the greenhouse effect, infrared energy is heat, or it's hotter. So as we get closer to that, we can think about this in terms of the amount of heat trapped within our atmosphere and the greenhouse effect. So in the greenhouse effect, we have our sun, we have our earth, we have our atmosphere. The sun shines in heat and light, and around half of it is bounced off of our atmosphere, but that other half is absorbed into our oceans, in our land, and some of it does try to bounce out of the atmosphere, but things like clouds or other greenhouse gases that are within our atmosphere also helps bounce it back into our atmosphere and keeps it within, and that heat that's traveling and stuck within our atmosphere is what keeps our atmosphere within really warm. So this is the greenhouse effect is based off of the idea of an actual greenhouse, where you would have your plants and vegetation within your greenhouse, and it just traps in heat really well. But now if we think more specifically about molecules and their structures, and how we were talking about 99% of what we have in the air is O2, oxygen, and nitrogen, N2. They have these are diatomic molecules with identical structures, where they're like balls in a string. So they, when heat bounces off of them, they wiggle around, but they don't absorb infrared heat energy really well, just because of the structure that they have. But now if we look at greenhouse gases like carbon dioxide, CO2, water vapor, H2O, and methane, CH4, they have structures molecular structures that are more flexible and they can wiggle around more and they can have many more ways to vibrate and rotate, so they can hold in heat, infrared heat, really well. This absorption spectrum of CO2, or how well CO2 can hold in heat, was measured by John Tyndall in 1863. It's always nice to give credit where credit is due. So now if we think about greenhouse gas and a greenhouse gas effect and how heat is held in, it's if we think about doubling CO2, what does that mean in terms of increasing heat over time? So say we have a Christmas tree light for every square meter across the earth. For every square meter, there's like 4-watt Christmas tree light, and that's what it would be equivalent to if we doubled our CO2 concentrations. And at first you would think it's probably not, it doesn't seem like a lot, but if we have this one Christmas tree light for every square meter that's on for 24 hours a day, 7 days a year, 365 days a year, this is a lot of heat added over time, and we would get warm pretty fast. And doing this would make the surface of the earth warmer. This was coined and measured by von Arrhenius in 1896. So these concepts aren't new. We're just seeing the effects of climate change and warming of the earth more now. So all these calculations and all these concepts aren't new, but yeah, we're just seeing it happen all now. So one common myth is that people are getting worried about climate change because it's getting warmer lately. And while that is true, this is data from Mauna Loa. This is the difference in temperatures in degrees Celsius as it increases over time. And generally it is getting warmer, so it is true. But this is not exactly why we're worried about climate change. It's because we know that if we add heat to a system, it's going to get warmer. And along with just adding heat, if we have different ways to trap in that heat really well, like greenhouse gases, then we know that the system is going to get warmer and warmer really fast. So this is not exactly, there's just more detail that goes into climate change than it's getting warmer. We just know that adding heat into a system, it's going to just make things warmer even faster if we have greenhouse gases. So if we're looking back into the past, over the past 420 years, atmospheric CO2 had varied around 180 to 280, and some ways that we can look at CO2 concentrations in the past is through ice core samples. And in ice core samples, we can see that there are ranges where we have periods of time where the Earth is actually supposed to go through a cooling or an ice age. And this is pretty consistent over time. But if we look into the present, since the Industrial Revolution, CO2 concentrations have been going up by a lot. So in 2016, it was measured that when we are actually supposed to go through a cooling period right now or getting close to an ice age, we have passed the 280 ppms and have reached 400 ppms in CO2 concentrations. So this is measured from the Mauna Loa Observatory in Hawaii. Mauna Loa Observatory is this. It's up on a mountain where there's very little light pollution, air pollution from surrounding buildings or land. So this observatory records CO2 data, and this is where we got this graph from. So now looking at human impacts, specifically at CO2, if we're thinking about CO2, one of the main ways that CO2 is released into our atmosphere is through fossil fuel burning. So industrial power generation is responsible for 25% of global greenhouse gas emissions, and that is through converting fossil fuels or coal into energy that we can consume. So not only does fossil fuel burning or industrial power generation contribute CO2, but other ways that CO2 can be added is through driving your car, or if your home doesn't have solar or wind energy, then it's most likely using fossil fuels to run. Another way that we add greenhouse gases is through CH4 or methane via livestock because we eat a lot of meat on Earth. There is agriculture and land use are responsible for 20% of global greenhouse gas emissions. So there are around 1 billion cows in the world, and each cow makes around 100 kilograms of CH4 or methane per year. So that is 100 billion kilograms of CH4 a year. And greenhouse or this methane is from agriculture or from cows or produced by cow farts. So that's but along with livestock and greenhouse and like cows, another way that methane can be introduced into our earth is through landfills. If you don't separate your recycling and your compost, if you have food waste in your landfill and it's trapped and it's not properly separated, then the decomposition process doesn't like go through, and CH4 methane is can be released from landfills. So they're both CO2 and CH4 are both problematic, but they vary slightly where CO2 has a longer lifespan, but it doesn't trap in heat as well as CH4. But even though CH4 or methane doesn't live or stay in the atmosphere for long, it does hold in heat really, really well. So they are both very problematic greenhouse gases. And it's not that, you know, yeah, these are just two of the many types of greenhouse gases that exist within the atmosphere, but these are one of the two main ones that we're concerned about. Oh, I guess one good thing to note is that we're actually moving away from fossil fuel burning and coal in general, because coal is a finite resource and countries around the world know that we can't rely on it forever because we're eventually going to run out of coal. And so there's a bigger shift to solar and wind energy, but that's like a hopeful thing to think about. And it's also getting more expensive too to invest in coal. So that's one nice thing to think about when we think about CO2 or fossil fuels. Yeah. Right, so the Lab 9 exercise, we are going to look at CO2 and within a closed system where there's no CO2 in its atmosphere versus a closed system where we add greenhouse gases or CO2, and looking at the changes in temperature over time. How does adding our greenhouse gases affect the data or affect the system that we are looking at? And then we're going to make one graph looking at those changes in temperatures, and then answer some questions in the Word doc that we can find in the Lab 9 Canvas page. So we can now go to Canvas, and I can show you what we go to next. So if we go to our Lab 9 Canvas page, this is background information on today's lab. And if we scroll down, there's 3 videos. There's this 2-minute video that we're going to watch together about greenhouse gases and the molecular structure of greenhouse gases. There is a more in-depth video that goes into detail, more detail about greenhouse gases and their structures. And if you wanted to watch that, it's here. And then our lab demonstration video, where we're looking at those 2 closed systems, one with CO2, one without, and the changes in temperature over time. Yeah, this middle video, it's around 8 minutes long. It's optional, and you can watch it in your own time if you wanted to, but we can watch this first video together now.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18°C. And even deadlier, they range from -170°C during lunar night to 100°C at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team over at Kurzgesagt for doing the animations in this video.
So that was a really good overview of what we were talking about, overall greenhouse gas effect and the different types of molecular structures of greenhouse gases. But now we can watch the lab demonstration video made by our lab manager, Darren, on a closed system with CO2 and one without. It's around 5 minutes long, and we'll be using data from this lab to make our graph afterwards.
In this video, we will be doing a walkthrough of the experimental portion of the ENVS 100 lab on the greenhouse effect. Our setup consists of 2 flasks with rubber stoppers in each, as well as 2 digital temperature probes, a desk lamp with a 60-watt light bulb, a little bit of water in each flask, and finally, a little bit of dry ice. One of our flasks will serve as a control environment, representing the Earth's natural greenhouse effect. The other flask will represent a greenhouse effect that has been amplified by an increase in concentration of greenhouse gases, in this case, CO2. The rubber stoppers will allow us to seal our environments, making them closed systems. The temperature probes will slot through a hole in the top of each stopper and allow us to collect data from inside of our environments. The lamp will represent the sun, giving off visible energy in the form of light, as well as infrared energy in the form of heat. The small amount of water in each flask will represent the oceans, and the dry ice will provide us with an increased concentration of greenhouse gases in our experimental flask. To summarize, starting from room temperature, we will be observing the differences in temperature between a natural greenhouse effect and a CO2-enhanced greenhouse effect when exposed to infrared energy over the course of 15 minutes. Temperature data in degrees Celsius will be collected every 30 seconds for 15 minutes. There are 2 important things to note in regards to our use of dry ice. One is that while we often think of gases or air as having weight, CO2 gas is actually heavier than the air we breathe, which is mainly composed of oxygen, O2, and nitrogen, N2. Here, I've added our dry ice, our CO2, into our flask, and as you can see, this little foggy area right here is sitting quite low in the flask. This is all of the solid carbon dioxide returning to its gaseous phase. As it sits low, and as it's heavier than air, it pushes air up and out of the flask. This allows us to assume that we have collected a fair amount of CO2 in our flask as we run our experiment. The other thing to note is that CO2 in the solid phase as dry ice is only possible due to extremely cold temperatures, hence the name dry ice. That means, as you'd likely guess, when we add dry ice to our flask, it will lower the temperature of the flask significantly. To maintain our experimental design, we will wait for the CO2 enhanced flask to return to room temperature before we begin collecting data. Okay, so it's been a few minutes, and the CO2 enhanced flask has returned to room temperature. Both flasks are sitting at just about 22.9 degrees Celsius. So once again, our data probes are set to take a temperature reading once every 30 seconds, and we will begin running our experiment over the course of 15 minutes.
So the blue line at the bottom is our control flask, add our dry ice into the blue, and the green line at the bottom is our CO2 flask with our dry ice. And it's already stating that there's a difference in temperatures as it's getting up, and you can see about that. There's
And that's our 15 minutes of data collection. The data will be exported as an MS Excel file and posted on the lab Canvas page.
So I think the video was too loud, but I was just saying that this, the blue line at the bottom is our control flask with no CO2. And then the green line on top is our CO2 enhanced flask. And already that there's a change in temperature, or the difference in temperature between the two. And you can see that over time. But yeah.
You will be using this data to create graphs and answer questions as assigned by your lab instructor. This concludes the ENVS 100 greenhouse effect demonstration. Thanks for watching.
Great. So the data that we're going to be using to create our graph is actually, it's right underneath the lab demonstration video. Past the lab 9 questions, right underneath that is the lab 9 data. You can click on that and download it by clicking on this black arrow on the side. When you've downloaded your Excel sheet, it's going to look like this. So our column A is our time. We've recorded our data every 30 seconds for half an hour in this data sheet. So this it's a data point for every 30 seconds for half an hour.
Hey, Maggie.
Oh, yes.
We can't see it.
Okay. One moment. Here you go. Can you guys see it now?
Perfect. Thank you.
Okay, awesome. Right, so column A, time, 30 seconds for 30 seconds, a new data point is collected for 30 minutes. Our column B is our control flask, where the temperature within that flask is recorded every 30 seconds. The column C is our CO2 enhanced flask. Column D is our change in control over time. So as our temperature increases from each 30 seconds to the next 30 seconds, this is our change. And our column E is our change in our CO2 enhanced flask. And thinking about heat budgets, this is how we calculated D and E. Change in heat, so the amount of heat going in minus heat going out. We're going to want to just make a graph looking at the change in heat for both of these, control and the CO2 flask over time. So to do that, we can select column A for our time. It's different on different computers, but to select columns that aren't next to each other, I would hold down the command key. It might be the shift key on your computer, but I'm going to hold down my command key, select column D, and select column E. I'm going to release my command key, and now these three columns are selected. And now I'm going to go to the Insert tab, right next to the Home tab in the top. And in the middle, right next to where there's recommended charts, I'm going to select the scatter option. So this XY scatter button right in the middle. So we have a lot of different options. So we have just regular XY scatter. We have scatter with smooth lines. I'm just going to click on the scatter, this very first option here, to get our scatter plot. Did anyone want me to go over that again?
Yes, please.
Okay, sure. So select column A and hold down the command or shift key on your computer to select column D and E. These are the three columns that we want to look at. I'm going to release my command key. And right next to the Home tab in the top left, there's this Insert tab. And near the middle, where there's recommended charts, you're going to look at and select the scatter option. And this very first choice of XY scatter, this is what we're going to select. Does anyone, I know like for the past lab that I taught, there were some changes in their chart where it doesn't look exactly like this. Did anyone have any questions about this chart here so far?
Yeah, mine doesn't look like that. It has like a lot of series and then like all the points are on one line. Like it's not looking like that.
Okay. Can you share your screen?
I'm on a different laptop for Excel because my laptop I'm zooming on doesn't
Okay.
have.
Yeah. I guess I know for another student, it was that they didn't select like the label or the title for each column, and that's why there was like a slight change, or like the titles weren't coming up and it was only saying series. So instead of like maybe manually selecting the columns, just select the whole column by clicking on the letter at the top. It might be that it might also be that I know another person was selecting like a different type of chart instead of a column chart. So under the insert, they were selecting recommended charts instead. Yeah, I guess just make sure to click on the XY scatter option. And this very first XY graph is what we're making.
Okay, I'll try.
Yeah. Yeah. Did anyone else have any other questions about this graph so far? Okay. So now that we have this graph, we're just going to add in our X and Y axes titles. So we're going to select our chart. And if our tab at the top isn't under chart design, we're just going to select chart design. And all the way on the left, we're going to add chart element. So we'll hover over axes titles, and we can add in both our primary horizontal and primary vertical. We'll just add in our primary horizontal, our x-axis titles for now. So at the bottom, when it shows up on our graph, we can just change it to time in seconds, because this is each of these data points is 30. It's every 30 seconds collected over half an hour. Now we can add in our y-axis title, where if we go back under add chart element on the side, we can hover over axis title, and right underneath primary horizontal, we can select primary vertical for our y-axis. And when it shows up on our graph, we can just change this to change in temperature in degrees C. So our blue dots on our graph is our control, where we didn't add dry ice into it. It's just air. It's an empty flask with water, and we've been collecting that change in temperature over time for half an hour. Our orange is our CO2 enhanced flask, and that's the one that we added our dry ice to. There's a couple of different ways that we can add CO2 to a system. It could be either through like dry ice, or it could be through mixing vinegar and baking soda. And it doesn't have to be only through driving a car that we make CO2, but you can see that over time, the CO2 enhanced flask, it's getting increasingly hotter and hotter, and the range in temperatures between these two flasks, they start to be more dramatic, more towards the end. But this is basically the graph that the one and only graph that you're making for this lab. And you would change the chart title to something more descriptive, like the difference in temperatures between CO2 enhanced flask and a control flask over time, something like that. But you would change the chart title to something more descriptive, and I will let you all do that on your own. But how's everyone with the graph so far? Okay, great. So now we're going to answer some questions on the Canvas page for that one Word doc that we'll be turning in. If we go back to Lab 9 Canvas page, right above the Lab 9 data, we have Lab 9 questions and assignment. We can download that, and it will give us a Word doc with questions. The first part we'll answer now, but if we open this link, it's going to look like this. So we have our first question: using the data collected from the experiment, create a scatter plot of change in temperature over time. And that was that one graph that we made together in Excel. So when you submit your responses to this Word doc, you would just also submit that Excel sheet. For question 2, write a brief summary of the results of your experiment. What is the difference in temperature at the start of the experiment, at the end? So here you would just write a couple sentences on the lab demonstration video that we saw together, where we had the two different flasks. We had one with CO2 added through dry ice, like temperatures recorded over time, and just talk about the methods and the materials for that, and just a couple of sentences here. For question 3, in your own words, describe how the greenhouse effect works. So you can talk about how in a closed system, where in our greenhouse or on Earth, the greenhouse effect takes into consideration our atmosphere, which traps in heat really well from heat which is introduced through the sun, and greenhouse gases within our atmosphere is what traps and holds in heat and increases temperatures over time. So a couple sentences on that in your own words. Question 4, greenhouse gases are able to absorb infrared heat energy. What allows them to do this? This is referring to what our video and in the lecture portion of this lab, we were talking about the different structures of CO2 versus other molecules in our air. Like oxygen and nitrogen, they have a very identical symmetrical structure, but greenhouse gases have a structure that is more flexible and can trap in heat really well. So this is what you can answer for question 4 in a couple of sentences. And for question 5, compare and contrast the model of the greenhouse effect that was created in lab to that of the Earth's greenhouse effect. So comparing a controlled experiment where we're only adding CO2 into our flask, if you think about the Earth's greenhouse effect, there's a lot of other greenhouse gases that also exist. So not only does CO2 have an effect on our atmosphere or on heat within our atmosphere, but there's also methane or water vapor, and there's a lot of other factors that also change like the climate in an area. So this is what you can write here. Now, if we're moving on to question 6, we in the lecture portion of this lab, we looked at Mauna Loa Observatory CO2 collected data. This is the website to get to that data that we can look at too. So what we're going to do for question 6 is just compare the CO2 data, or the amount of CO2 in the year that you were born, and the amount of CO2 that was collected just yesterday. So when we select and click into this link, it will take us to the Mauna Loa Observatory collected data website, and we will have our time across our x-axis and our CO2 concentrations in ppm along our y. So to zoom in to a certain amount of time, we would just click and select, and that will zoom into whatever time period that we wanted to look at. Let's say we wanted to look at data from just yesterday. I'll just select this time all the way at the very end and zoom in there. There's a chat. We can't see the screen. Oh, okay. I guess let me reset that. Yeah. So here we are. So sorry about that. Right. So time is across our x and CO2 concentrations across the y. And we can zoom in to a certain time period by just clicking and selecting and scrolling along our graph to see that CO2 concentration at that certain point in time for that day. So it's concentrations have been collected every single day, but you're just comparing, say, your birth year, the concentration of CO2 then, and to the concentration of CO2 that was just collected yesterday. So I'll just click and zoom in to this small portion and say for yesterday, April 28, CO2 concentrations was 419.75. So you can write that down for that question and then zoom in to a point in time in your birth year. So for your birth year concentration, let me just reset Zoom. If we see that, let me just zoom in a little bit more. We see that there are these ranges in CO2 over time, and that correlates to the amount of, along with the amount of CO2 that's released at that point in time. It also correlates to different seasons within the year. So right now we can see that as of April, we are at this high peak in our graph. And for your birth year, we would also try to find a similar point in time for that year. So we are at near the high peak of 2021. So say it would be more comparable to look at data near the high peak of your birth year instead of one of the lower data points. So that's how you can choose your second data point, and then just record that for that question and talk about the difference between those two points in time, those CO2 concentrations. Right. And you can always reset Zoom to look at the overview of the entire graph again. And that is basically how you can answer that question. So now we go back to our Word doc. For questions 7, 8, and 9, we are going to be doing some calculations. So if you're more comfortable doing calculations or doing math by hand, you can do that. You would just take a picture of your work and insert them into the Word doc here so I can check your answers that way. But another way to do calculations or show your work is through using the equation tool in Word doc. But first, let me just read question 7 to you all. In 1960, the concentration of CO2 in Earth's atmosphere was 320 ppm. In 2010, the atmospheric CO2 concentrations were measured at 390 ppm. Calculate the average annual increase in CO2 between 1960 and 2010. Show your work. So we're comparing 1960 data to 2010 data. So to start our equation, we can just click anywhere in the bottom of wherever we want our equation to start. So I wanted to start in the next line. So I'm just gonna select this next line here. We're gonna go right next to the home tab, there's an insert tab. And all the way on the right-hand side of our toolbar, we have our equation, insert an equation selection that we can make. So we can just click on that and type our equation. This box is going to pop up in our Word doc. And since we're looking at the average annual increase in CO2, we can start off by putting in a fraction. So in the middle of our toolbar, once we put in our equation, we'll have this fraction symbol. And we'll just select stacked fraction, this very first option. So we're looking at 2010 versus 1960 data. So at the top, we'll put in our CO2 concentration at 2010, which is 390 ppm. We'll subtract that from 320 ppm, the concentration in 1960. In the bottom of our fraction, we'll look at the difference in years. So from 2010 minus 1960. We'll just continue and put in, we'll put in another fraction and just go through this step by step. So to add in another stacked fraction on the end here, we'll just go back to this fraction tool in the toolbar and then select that very first stacked fraction option. And 390 ppm minus 320 ppm is 70 ppm.
Excuse me, Maggie. How did
Yeah.
you add that other fraction?
So you would just go wherever you ended the end of your equation to. Say if we wanted to just put in another fraction at the end here, we would go back to this fraction button.
How did you get the equals in there?
You can just type in equal on your keyboard.
Okay.
But if not, there's also an equal sign that you can select here. So along with like equal, not equal to, multiply, divide by, these, you can add those here from selecting the top of your toolbar, but it's also on your keyboard. So
Okay.
yeah. If you wanted to add your another fraction, you can just click wherever you want to add your new fraction to, and then go to this fraction button in the middle of your toolbar. And that very first stacked fraction option, you can just select that and it should pop up on in your equation. Yeah. Great. So, right, so the difference in years from 2010 to 1960, we would just put, that's 50 years. And we'll keep this as a fraction so we can keep our units in the same order. So 70 ppm minus 50 year, or divided by 50 years, is going to be 1.4 ppm over every year. So from 1960 to 2010, every year 1.4 parts per million CO2 is added. And this is the general setup of how you can find your average annual increase in CO2. And this is how you can answer question 7. For question 8, we're assuming the annual rate of CO2 increase calculated in question 7. It says question 6. It's actually just referring to the question before for question 7. We're assuming that the annual rate of CO2 increase stays the same. So our 1.4 parts per million per year, it stays the same. Now predict the concentration of atmospheric CO2 in the year 2100. Use the 390 ppm in 2010 as your starting point. Show your work. So we're still looking at 2010 and then just bouncing off of that and keeping this 1.4 ppm of your annual rate of increase the same. So we can first start off by calculating the difference in years. So we can insert another equation by just clicking on this next line, going back under the Insert tab in the top in our toolbar, and all the way at the end, we'll just select Equation. When it shows up here, we can first show that we are looking at the difference in years, so 2100 minus 2010 is equal to 90 years. So that's our time frame. We're looking at these 90 years from 2100 to 2010. Now we know we're still looking at this annual rate, 1.4 ppm per year, this rate of increase, but now we're looking at it over 90 years. So let's say we want to add another equation and just show our work again at the bottom on this next line. So I'll click on this next line, go back under the Insert tab at the top. All the way at the end, I'll select our equation option, and then I'll just put in another fraction to show our 1.4 ppm per year. So I'll put in another fraction by clicking on this type your equation and then selecting this fraction button in the middle of our toolbar and selecting again that very first option of stacked fraction. I'll retype in 1.4 ppm over year. You can add your multiplication sign by either typing in X, or you can select this multiplication sign in your toolbar. In the middle here, we have equals, multiply, divide by, some less than, greater than signs, and all of that. We'll select just the multiplication sign because we're multiplying 1.4 ppms per year by our 90 years, our time frame. So we'll just type in that now. So already if we look at our equation, we know that 90 years, when a number is by itself, so any number by itself is automatically a fraction over 1. So our years would cancel out and it would leave us parts per million as our final unit. So if we wanted to multiply 1.4 ppm by 90 years, we're going to be given 126.0 ppms. And this is our the amount of CO2 added from 2010 to 2100 within these 90 years. So this is from 2010 to 2100. And this is the amount of CO2 added 2010 onwards. But now we know from our past question that before 2010, that year, there was 390 ppms of CO2 that already existed. So we'll just add this already existing 390 ppms to our 120 ppm that we just calculated from 2010 and onwards. So we can first just select this next line that we want to add our equation to, go back under the Insert tab, and all the way on the right-hand side, we'll just insert an equation. So we know that 2010, the CO2, the amount of CO2 that we know that existed then is 390 ppm. And we're going to add that from 2000, the amount from 2010 to 2100, which is the 126 ppm. And that is going to equal 516 ppm. And this is looking at using the annual rate of increase of 1.4 ppm per year. And this is our final answer. Let me pull that. So that is how you can answer question 8. For question 9, it's the exact same setup as question 8, but now we're thinking, well, what if the amount of CO2 added per year it actually increased? What if there's more CO2 that's added every single year? And so the new rate of increase, instead of it being 1.4, is 1.9 ppm. And this would just be your new rate of increase that you would be using. The setup to do the calculation is exactly the same. You're still using 390 ppm as your starting point in 2010, but if you just refer to question 8, the process is the same for question 9. You're just using 1.9 instead. Did anybody have any questions about how to do these 3 problems? Okay, so for question,
what was? Yeah, are we going over 9 now?
Yeah. So question 9, you're doing on your own. Yeah. The setup is exactly the same as question 8. But instead of using the 1.4 ppm per year, you're now using the 1.9 ppm. So what if the amount of CO2 added or to Earth, or that we're producing every year, what if it increased and we're now producing 1.9 ppm? We're still looking at the exact same time frame from 2010 to 2100, and we know that in 2010 there's still that 390 ppm as our starting point. So you would still add your 390 ppm to whatever number you get with your new rate of increase, but the setup is exactly the same. You're just using 1.9 ppm here instead.
Okay.
Okay. Okay. So our final question on our Word doc is, what do you predict will happen to the global temperature of Earth as more CO2 is added to the atmosphere? What are some implications of this? This is a free question for you all. What do you think would happen if we have more greenhouse gases to our atmosphere, when we know that greenhouse gases, they hold in heat really well and increases the temperature of on Earth? So this is, you can answer with a couple of sentences. What do you think the implications are if the amount of CO2 or if the amount of greenhouse gases are continuously increasing, which we can see now? Did anyone have any questions about any part of this lab, either the Excel portion or on any part of this Word doc? You can always stay afterwards and I can answer them too. But if you did have any questions about your grades, late work, or any quizzes that you didn't get a chance to take, you can just talk to me about that too. But this is Lab 9. You're just turning these responses along with your Excel graph, and that is basically it. So I hope you all have a good rest of your day, and I will see you all next week.
Thank you, Maggie.
Thank you.
Thank you.
Thank you.
Maggie, could you help me with my